Welcome again to MIS 5000, since we only have grad students, special topics in MIS, Python programming. In this video, we're going to go through the material for Module 1, which is our course introduction. Again, I'm Dr. Carl, and I will be your instructor this semester. So welcome. Our course is completely online. It's 100% asynchronous. I will have office hours over Collaborate Ultra on Tuesdays and Thursdays from 12 to 1, and also by appointment. And my email is kcarl@govst.edu. And this is Bubba, who's looking very dapper in his tie after getting groomed. He's one of our golden doodles. So let me take a minute to introduce myself. So I'm Dr. Catherine Carl. I'm originally from a south suburb of Chicago, so Orland Hills, Illinois. I received a Bachelor of Arts in English Literature from Illinois Wesleyan University, which is a small private liberal arts school in Illinois, in 2008, and I received my PhD in management with a concentration in management information systems from the University of Arizona in 2014. For my dissertation work, we put together 3 papers in which we designed a system that bicyclists could use to find a minimal perceived exertion path through the United States. So this involved first creating mathematical models for perceived exertion based on surveys from bicyclists at different levels of expertise. This also involved the work that went into eventually a patent where we turned a basic Google map into what we considered a topographical graph. So where each node essentially indicates a change in incline, which represents a change in perceived exertion. So that process produced a patent with my advisor, Dr. Moshe Dror, whose background is in operations research and applied mathematics. So my minors were in computer science as well. So that is kind of where I am along the math to engineering spectrum. I'm kind of more in the math and computer science camp. The last part of the dissertation, I actually designed and implemented the system. I used some Python that would take in a source node, a target node, and points of interest, and produce a route of minimal perceived exertion based on expertise level of the cyclist, specifically in California. So this involved integrating several different data sources, including the OpenStreetMap data, which is free and available. So the data for the United States actually came around finally in 2012, which is exactly when I needed it, as well as I sent a terabyte hard drive off to the U.S. Geological Survey, and they returned to me 500 gigs of elevation data for the entire United States, which was interesting to work with. So these are very large data sets. The OpenStreetMap data had 43 million nodes. So when you talk about big data, that's kind of getting there, which even at this point isn't that large. But essentially there had to be an algorithm designed and connected to all these sources. There had to be a database implemented, and so I was the one that actually did all of this under the supervision of my applied mathematician advisor, Moshe Dror. I have been teaching all kinds of related technical courses since graduating. So I've taught introductory management information systems. I've taught database management several semesters at different universities. I've taught business analytics at a couple different universities. Now data visualization. I've also taught backend development and operations management. I have been teaching programming since 2017. That was the first time. I guess really more like 2014. So we did some Visual Basic in one of the introductory MIS classes that I taught initially. But when I got to Incarnate Word in 2017, I found myself in a situation where the students really hadn't been worked with well enough to be able to adapt to learning something so technical like programming. And it kind of opened my eyes to really the state of programming education in general. And it made me think about how I had learned programming and really to think about, how could I improve this? How could I make this accessible to students who are not coming from a technical background that maybe are in the business school? And so over the course of several semesters since then, so 2017 on, I taught Python, I taught C#, and I taught Java. And I slowly but surely came up with the system that you're essentially going to see throughout this course, which involves start with logic and flowcharting, and then ends with actual applications. As a tenure track professor, I also conduct research in the area of video games and education and technology and learning. Actually, a paper I did with some friends that played League of Legends with me is my most cited paper. It's related to Twitch and learning from experts and novices. If you're interested in reading it, let me know. I can send you a link. So I'm also very happily married. We just got married a little bit ago. We have 2 golden doodles and 2 cats. I enjoy playing video games. Most recently, I got a PS5 and I'm playing Demon's Souls. I really enjoy reading, music. So I play piano, I sing. I grew up playing trombone and euphonium. And then I also do aerial fitness for fun. So that is probably more information than you wanted about me, but I figured giving you, a detailed explanation of my background would help you understand kind of where I'm coming from, the teaching philosophy that I have, and why I'm presenting programming material in the kind of special way that I'm going to present it. It may be unlike anything you've seen before, so you'll have to let me know. But I've been in the trenches working on it for quite a while. I've seen great results with students who didn't believe when they walked in the classroom that they could do any of it, and then walked out some of the most strong, skilled programmers I've seen. So it really is about developing that mindset. So for this module, we just want to be able to describe the policies outlined in the core syllabus, and then also to define and describe the importance of a growth mindset when you are programming or thinking about programming. So before we get into that, let me go ahead and introduce the course textbook and materials one more time. So our book is Automate the Boring Stuff with Python. You can purchase it on Amazon, but it is also free on the internet at this link here. There is an optional textbook on syllabus as well that is a program language independent book just about logic. If you'd like to check that out, you can feel free to. I'm going to pull some information from that as well. So what technology are we going to use? We're going to use the Microsoft Visio 365 flowcharting tool, which is free with your GSU account and launches actually in the browser. You can use another option, just make sure that your shapes are consistent with those used in the course. We're also going to use Python 3 and Visual Studio Code, which again, you are welcome to use a different IDE. I really don't care as long as it's not in a browser and that I can, interpret the code just fine. So, but in my videos, I'm going to use Visual Studio Code. You're welcome to get all these things now, but you don't have to. If you would prefer to wait, I will be going over the installation and use of all of these things as we need them. Okay, so what is programming? I kind of want to talk about this in different ways and give you my philosophy. So Al Swigert in Automate the Boring Stuff, he basically has 4 different things, statements that he considers to be programming. So the programming logic. So we can simply do tasks. So like computation, we can add things. That would be an example of this statement, do this, then do that. So maybe we take some input, we get a couple variables, we add them together, and then we print them to the screen. That's just simple, do this, then do that. Sometimes we want to do things if conditions are true or false. So we can talk about conditional statements. If this condition is true, perform this action. Otherwise, do that action. So I'm going to use this silly example of a business that sells donuts. So you take in the number of donuts that the person wants to buy as input, and then use a conditional to say, if they buy more than a dozen, they get a discount. And if they don't, then they don't. So that's another type of programming logic. We can also perform tasks repeatedly. And if you're familiar with programming, you'll understand that this is basically I'm talking about a loop. Do an action a specific number of times. So this is going to be, ahead of time how many times you want to do the action. So for example, I'm going to use a silly example, but let's say you have a child and they're going in the United States, we do something called trick-or-treating. Basically, take the children door to door in the neighborhood, visit the houses on Halloween, which is, we dress up in costumes and that kind of thing, and the kids will get candy. So there is a set number of houses in the neighborhood, and so we will just keep performing that action. We show up to the door, we knock, the kid says trick or treat, they may or may not get candy, the door may or may not be answered, but the point here is that we know ahead of time how many times we want to do that task. In this case, it's bound by the number of houses in the neighborhood. Finally, we have a different kind of loop, and that is we keep doing an action until a specific condition is true or false. So this is what's referred to as sentinel controlled loop. So if you think about when you go to the self-checkout at the grocery store, I think most of us have done that, that basically it's going to sit there and wait for you to scan an item until you say that you want to pay. So it doesn't know ahead of time how many items you're going to scan. It's going to sit there and wait. The sentinel's basically going to keep checking, okay, did they push, finish, and pay? And if you haven't, it's just going to keep waiting for that scan, that input. So it will keep a running total of the items that you are purchasing. So there are some other things. We can talk about data structures. We can talk about more the nitty-gritty of syntax, but essentially programming is about solving problems. So, and before you can do that, you really have to understand the kinds of logic that are involved with solving problems, because that is really what's at core. You can know all of the syntax, you can know all the parts of the language, but if you don't sit down when you are introduced to specifications at the start and think about, okay, well, what needs to happen in a very human way, then it's going to be very difficult for you to actually write the code. What you'll find is that, you might get lucky and you might kind of, have practiced enough that you know internally what kinds of logic you're looking for. But usually you have to sit for a while and kind of think, okay, if I'm going to write a program that plays rock, paper, scissors with me, the computer plays rock, paper, scissors with me, you really have to sit there and think about, okay, how does rock, paper, scissors work? You have to start there. And then you can kind of plug in the syntax. So what I want to do, one of the goals in this course is to really separate the two things. So you have the programming logic and you have the syntax of the language. If you understand the programming logic, learning any programming language, whether it's Java, C#, etc., becomes quite simple, because then you're just learning the language. You're not learning the logic as well. So I think that this is the appropriate place to start. And my hope is that you'll see that as the course progresses. A question I get asked a lot about programming is, do I need math? And I have a little picture of solving Sudoku here. So do I need math? Yes. Not necessarily directly, but certainly you have to be able to think logically, to think mathematically in order to solve problems with algorithms. So for example, if you want to solve the Sudoku, you have to be able to understand how the algorithm works and work through it. So it's not direct computation necessarily, but you do have to be able to think mathematically. So why bother learning Python? I think most of you kind of internally know that it's in demand in industry, so you don't really need me to talk about why, but I will just for a second anyway. It's a very versatile language that you can do so much with Python, and it's pretty easy to work with. It's one of the most human-friendly, readable languages that exists. The hardest part of Python, I think, for a beginner is really getting used to casting the data types. Because in Python, you don't declare what specific type a variable will be. You kind of have to force it as you go. Once you can get past that, I think it becomes easier, but that's definitely a skill that you're going to need to work on once we get there. And Python, to me, it's not used to develop large-scale applications. That's not what we use Python for. If you're designing a game, probably use Unity, C#. If you're designing an operating system, you use C, heavy-duty things like that. Python is, okay, I have a text file full of addresses, HTML that I scraped from the web. I don't want to manually parse it. I want a program to just go through and scrape the addresses for me so that I have them in a CSV. And with Python, you can do that. Python is kind of a one and done situation where you can just write scripts on the fly for things that you need. It's also very easy to do things like, for example, you have the application here of the Twitter sentiment analysis. That Python's very friendly with APIs connecting to different applications where you can get data and then work with that data. Yeah, for analytics, I think Python is the perfect language. It's not too heavy, but you can do so much with it. And the focus is really on the applications, less so than necessarily, clean code or highly optimized code. So that will not be the approach. If you've studied, for example, computer science topics like big O notation, we're not going to worry about that here. I mean, we may to some extent try to optimize things, but this is going to be a quick and dirty type of programming. So one thing I want to talk about is errors, making mistakes, hearing from the compiler that it is unhappy, that you've done something it doesn't like, and or that you've run your program and it works, but you didn't get the output that you were wanting or expecting. So I'll lead this by saying, first of all, that the computer, whatever you're working with, will always do what you tell it to do if it's working, but it may not always do what you want it to do. So the goal is obviously to get those things in alignment, that it is both doing what you tell it to do and that what you tell it to do is what you want it to do, because it is not smart. So you are the smart one. You're the one telling it what to do, and it is just trying to get by. It's letting you know when things don't add up and just asking politely for you to help it get along. You may already have a comfortable and strong attitude towards making mistakes. It may not bother you, and that's fantastic. This note is mainly, for people who get very upset when they see errors or who think, it's a reflection of their own personal self-worth. It's not, okay? So something just didn't work. And what I want to offer to you is what I've seen students do is essentially they put into one box programming. They say, this is the programming box because everything's working. When everything's working, I'm programming. I ran it. It worked. I'm programming. And then they keep this other box where they've made a bunch of errors and they kind of just shove it to the side and they say, well, that's not programming. That was just, a bunch of stuff I needed to do to get to the thing that I wanted to do. But not true. I will challenge you to think of programming as both when things are going well and when things are not going well. So the struggle is really part of the process. Making mistakes is part of the process. It's information when the compiler yells at you. And it's useful information for the most part. Sometimes it's not, but for the most part it is. So when you encounter an error, if it's the kind of thing that makes you seize up, take a deep breath, maybe take a walk, realize that, it's part of the process and you're going to get through it. So what are your options? Let's take a look at this error. So we have traceback, most recent call, last PyShell line 1 in module. Then we've got in single quotes 42 plus 3. And it's throwing this type error, can't convert int object to string implicitly. So this is kind of what I was alluding to, that Python's real specific about it needs help understanding what data type that you're using. And here, we're trying to, either the 3 also needs to be a string, so we can concatenate, or the 42 needs to be taken out of those quotes so we can add integers together. But either way, the point of this is that we have this type error. I know what it means, but I didn't back in the day. So what do? And this, again, may be something that you are already familiar with, but take the error, throw it into a search engine, see what you can find. And in the case of our course, what we're going to do is encourage this mindset toward mistake making by implementing what I'm calling Error Town, so that by posting your own errors and sharing them with others and seeing the errors of others, that it will help you realize that this really is part of the process, and you'll see, that you can collaborate on that and get through it as well. And specifically, the reason I want to use Error Town within the course is that there's a temptation to go to Stack Overflow every time something goes wrong. And if you are a novice, what's going on Stack Overflow may not make any sense to you. It will require more information. This gets kind of into that Twitch paper that I did looking at experts and novices. When you are a novice, you need information from other novices because you need it to come at the level that you're currently at so that you can better understand what to do next. And that's kind of what I'm hoping to get out of Error Town. You can, if you've never heard the song We Can Work It Out, I suggest you listen to that as well. I provided the link here. I'll put it on Blackboard. So here you can see the Google search that I did. I just copied the type error and I got some results. So these are actually Stack Overflow. And while I am commenting on Stack Overflow to say be careful, I'm obviously not saying never use it. We can see it says you cannot concatenate a string with an int. So in other words, you can't do the concatenate is just a fancy term for shove together. So we're not going to get 423 out of 42 in quotes plus 3, for example. You either got to change the 42 to an int or the 3 to a string. Get in the habit of looking for information about errors once you get them if you do not understand them. I've already talked a little bit about this, but again, in this course, what I would like to do, and this is not Python, by the way, you can probably tell, but is to separate in your mind the programming logic and the syntax of the language. The sooner you can do that, the easier it will be for you to focus on the problem solving before the coding. So I will tell you, I detest the term code monkey. I think it's derogatory. And it is not what I'm hoping for you. What I'm hoping for you is that you will be a problem solver. You'll be able to think about how something works and then how to explain to the computer how to make it work. So you're really communicating with the machine in a real way. So we need to focus on the logic before we get to the syntax so that those two do not get conflated. So let's talk a little bit about the growth mindset. I think I've talked about this in a previous course with some of you, but it's a very popular thing in K through 12 education actually, but hasn't really made it to higher education. So the growth mindset comes from research done by Carol Dweck, specifically in mathematics. And so basically the gist of it is that in a fixed mindset, in contrast, we tend to think that people have a fixed intelligence, and that you are just, going to be as good at a particular skill, so in this case programming, as you were sort of born into it. Versus a growth mindset, which essentially says that, no, it depends on the effort that you put into it. And so what Carol Dweck found is that when children were praised on their effort rather than their intelligence, that they were more apt to continue to work hard, and that, as you can see, if you actually work harder, then it does lead to higher achievement. So, and this also actually affects the higher achieving students in a good way as well, because I think what happens is with children who are high achieving, they think, oh, well, I'm smart, so I should be able to do X, Y, and Z. And then when they hit their first challenge, it really comes as a shock to them. They think, oh, well, maybe I'm not smart. So rather than, if you say, no, you're hardworking and yeah, you're intelligent too, of course, but that it is the effort, you're going to have to apply yourself. And so I just kind of want to make a note here. I think it's a good philosophy, and my hope is that I'll be able to use that and instill that with you in this course. So it goes along with the focus on mistake making and sharing that mistake making in a very transparent and collaborative way. So here is just a chart I included from some of the research that you can see. So students did difficult math problems, and it was found that if they were praised on effort rather than intelligence, that in the third trial, that the people that were praised on their effort actually solved more problems in that trial than those that were praised on their intelligence. In fact, those that were praised on their intelligence actually chose to solve fewer problems than they did in the first trial. So the focus on effort is really important. Before I conclude this video, what I would like to do is explain what I used to do in the classroom and what we would do if we were in the classroom. So I want you to think about, first of all, when was the last time that you learned how to play a new game? So this could have been a board game, could have been a video game, but just you encountered a new game. I guess board game kind of works better. I actually recently had an experience where I had to learn how to play Ticket to Ride. And nobody really talks about this, but it's hard to learn the instructions. Try to remember back to when you sat with friends or family and tried to learn a game. Somebody usually takes the instructions or wants to read them aloud. It's not very clear how we're going to internalize how the game works. It's a mess and it's hard. And there are different approaches basically to learning how to play a game. So what I used to do is I have copies of the board game Jumanji, And so I actually have the instructions here. What I want to show you is the board, and I want to show you the instructions and kind of what we did. So here is the board for Jumanji. So Jumanji is a game for those who seek to find a way to leave their world behind. So programming kind of is that as well, isn't it? Because you're sort of creating your own worlds within the lines of the code and then seeing them come into life when you run it. But I digress. So here we have the board. I didn't explain at all to the students how to play the game, which was of course very frustrating. But the point of the exercise was to work as a group to figure out how to play the game and then to play it. So it seems like a simple task, but I observed a couple of things. Let me go ahead and pull up the instructions. I'm going to link these on Blackboard as well. So they had paper copies of the instructions. They were divided into groups of 4, and they were given these instructions. So it comes with some die, and then what you'll notice is there's all this information, similar to any explanation of how a game works. I want to point out a couple of things. One of the key things to know first before you start playing a game is what I'm going to call the termination condition of the game. As we get into the programming verbiage, I'm going to use that term a lot. But what is the termination condition? In other words, when does the game end? How do we know when somebody won? And so here you've kind of got to look for it. Let me see if I can find it. See how to play. Tells you how to play. I'm going to go through one of the different types of spaces that you can land on and explain the activity that I gave them. So here, how to win. To win, be the first to reach the game board center by exact count and call out Jumanji. There are 2 ways to reach the game board center. So on your turn by exact die count after rolling the number die, or on a fellow player's turn by exact number count after moving ahead on a danger card. Okay, so some of this, we understand, some of it we don't know what a danger card is, etc., etc. But the point is, once we know the termination condition, we actually know when the game will conclude. So a really easy game to learn is, for example, Candyland, where basically you're just rolling a die and then you're advancing. Whoever gets to the end, wins. Whoever gets there first, rather, wins. So anyway, my point is that, first of all, it's difficult to learn how to play a game based off instructions. And I would like you to think about the specifications of a program. So for example, I need an application that takes in values, prices of different items, and then returns the total. Think of those specifications similar to the instructions of a game. Games really are a wonderful way to learn and think about algorithms and to promote algorithmic thinking. I think when we play games, we mostly just internalize the algorithms and then don't really reflect on them or think about them. But in this course, we're going to be doing quite a lot of that. I would like you to reflect on what you're seeing. What you'll see is those types of logic that Swigart presented in the book can all be found within games. You've got loops. You have players taking turns. What constitutes a turn? It's going to repeat itself. You have the conditional logic. So if, for example, let me show you what I had them do. So if we look at the board, there's different kinds of spaces. You have spaces that say 5 or 8. You have spaces with a rhino on them. You have these disaster spaces, and you have regular spaces. So each of the spaces comes with its own logic. So if you land on, for example, a rhino space, it says you may, if you wish, we have another conditional, if, put the rhino figure on the space directly ahead of any pawn, except on the game board center, to block that player from moving. It goes on to explain the block player remains on that space until another player lands on a rhino space and moves the rhino, or the blocked player rolls an even number on his or her turn. So essentially what you'll see is each of the types of spaces has its own logic. And so one of the requirements I had for that first class is that I would give each group a particular space to try and diagram. So basically the ask was, let's say somebody who's never played Jumanji shows up to the classroom. I want you to draw a diagram that doesn't have any, words on it. It's not textual, but a visual representation of what happens when you land on that space. And I got some very interesting things. Some were close to flowcharts, actually, which was nice because then we can progress in that way. But it's interesting some of the ways they chose to depict essentially programming logic in visual form. So that's where we're going to start. If you'd like to play Jumanji, let me know. Maybe I can set that up at GSU. But at any rate, just understand that, take some time to think about games you played and think about the different algorithms. Ask yourself, okay, what was the termination condition? When did the gameplay stop? And then what constituted a turn? What were we repeating each time? Were there conditionals? Were there special cases? You can even apply this to card games as well. So please take a minute to do that if you haven't already, maybe when the video is over. So I think that you'll find it interesting. But yeah, algorithms are embedded within games, and games, I believe, are the best way to understand algorithms in a very simple way. If you get into what are called classes and methods in other programming languages, I would say that toys and how toys are designed are a great way to understand methods and objects and classes. So we'll do methods in the sense of functions in Python, but we won't do the other things here. So make sure that you complete the syllabus receipt and discussion forum 1 by 11:59 next Monday. If you need to reach out to me, please do so. And then go ahead and just pop open Microsoft Visio in the browser and just check it out. You don't have to use it for anything in particular, but just kind of poke around, see if you can get familiar with it. Anyway, this concludes our discussion of Module 1. And if you have any questions, please let me know.